Okay, let's get started. Morning, everybody. Today we have Maya Engel as a speaker. Maya did her bachelor's at Tel Aviv University in chemistry, then moved on to Biogeochemical to do her PhD with Biogeochemical, working on the absorption of organic material and other pollutants on carbon nanotubes. And then moved to the States to pursue a postdoc, and she's now a postdoctoral scholar in both Stanford, working with Scott Fendorf, and in SLAC National Accelerator Laboratory. And she will tell us what she's been up to. So we're very happy to have you.
Okay, that will be. Okay, I hope this is going to be okay, this whole thing, but yeah, okay, great. So hi everyone, it's really fabulous being back in Israel. I haven't been here in 2.5 years, so it's quite a shock getting acclimated. So I'm really happy to present my research. I always like to introduce myself as well. As already said, I did my bachelor's degree in chemistry from Tel Aviv University. I've always been interested in environmental studies, and that's why I moved and started a master's in environmental chemistry with Beni Chefetz at the Faculty of Agriculture, and transitioned into a direct PhD, and that was focused on interactions between nanoparticles, organic matter, and organic pollutants. And at the end of my PhD, I decided I wanted to go more into soil chemistry, and that's why I joined the lab of Professor Scott Fendorf at Stanford University, working on heavy metal biogeochemistry. And after a 2-year postdoc, I transitioned into a neighbor lab at SLAC National Lab, working with the SLAC SFA, with Dr. John Barger and Dr. Christine Boy, focusing on hydrobiogeochemistry of floodplain systems. So it's been a really fabulous journey up until now, and I'm also interested to see what the next chapter has in store. I also like to acknowledge all the fabulous colleagues, collaborators, mentors throughout my studies that have been really indispensable. So I just wanted to say a big thanks to them, and also acknowledge the funding agencies that have made my postdocs possible. So what we're going to do today is we're going to start with a brief introduction to get familiar with some of the main topics of discussion, and I will present 2 research themes. The first is from my first postdoc at Stanford on spatial and compositional sediment heterogeneities and how they influence heavy metal retention. And the second theme is from my current postdoc at SLAC on the structure and dynamics of iron-rich colloids. And I will also devote some time at the end for future research directions. Okay, so the subsurface is a unique zone of Earth that's home to the biological and chemical reactions that sustain groundwater quality, soil fertility, and crop growth. And at the macro scale, the subsurface may seem to be homogeneous in nature, but as you increase the resolution further, you're more likely to find the heterogeneities that are hidden within. So I've been focusing on alluvial aquifers and soil systems, and in both of these, you commonly find both spatial and compositional heterogeneities. In alluvial aquifers, for example, you can find fine-grained sediments that are embedded within the sand. And in soils, you can find distinct soil horizons that may also encompass additional microsites and hotspots. And all of these spatial complexities give rise to various biogeochemical gradients or patterns. And you can imagine these to describe the degree of contaminant attenuation, the microbial community composition, or the redox environment. And all of these are going to influence the processes and reactions that take place within the subsurface. So one of the functions that subsurface systems provide is essentially their role in biogeochemical cycling of elements. So elemental cycling describes the transfer or movement of elements between various states or phases in our environment as a result of different biological or chemical reactions. And here I've highlighted some of the key elements that are cycled in our environment, those being nitrogen, iron, manganese, sulfur, and carbon, and all of these contribute to the natural balance that sustains soil and groundwater quality. If we take a bit of a more broader look at the services that elemental cycling provides, I've highlighted here in green some examples, those being groundwater storage and quality, the soil structure and fertility, which is linked to crop growth, agricultural practice and food security. And also, biogeochemical cycling is a means of maintaining the natural biodiversity and is a means of climate change mitigation. In red, I'm presenting some of the processes or practices that are further influencing the natural balance of that cycling. So we have intense industrialization and agricultural practice that lead into more fertilization, changes in land use, addition of organic amendments, contamination, and of course we always have climate change with its additional drastic effects. So all of these again are going to influence all the services that we rely on a daily basis. Okay, on to that. Okay, so apart from the key elements that are cycled that I just showed you, we have additional elements that are present perhaps at lower concentrations, such as heavy metals. And heavy metals are a natural part of our environment. Commonly, they are micronutrients and they help in the growth of crops and plants. And while their origin may be natural, it may be geogenic, we have anthropogenic sources that can increase heavy metal concentrations to hazardous levels in both the soil and the water. Now, heavy metals are really fascinating to study because they can exist in a variety of phases or states. So they may be dissolved, they can complex with organic compounds, they can come together to form aggregates or colloids. Upon interactions with mineral surfaces, they can absorb onto the mineral surface, incorporate into the mineral structure, and also precipitate to form various minerals themselves. And the phases or states of those metals are highly influenced by surrounding factors, such as pH, ionic strength, organic matter content, redox environment, soil structure, microbial community, and more. So all of these factors are going to influence the availability and the mobility of these heavy metals and their ability to participate in biogeochemical reactions. And as our systems become more complex, become more heterogeneous, we really must consider all the various factors that can influence the availability of those metals. So we're going to continue now with the first theme on spatial and compositional heterogeneities and how they influence heavy metal retention in a simulated aquifer system. So I'd like to emphasize the importance of aquifers because they store a great deal of the world's groundwater supply. So every process, every reaction taking place within an aquifer has the potential to influence groundwater quality. And as I mentioned, these systems are not homogeneous in nature. They encompass fine-grained sediments in a variety of shapes, sizes, and distributions. And these fine-grained sediments are commonly, they have very high clay content and organic matter, and also have high concentrations of reduced iron and sulfur. And because of their unique composition, they have the potential to influence the surrounding biogeochemical environment. And that's why we were interested to ask, how exactly do these fine-grained lenses influence the biogeochemical conditions within an aquifer system? And furthermore, how will they influence the retention or the behavior of heavy metals? Here we have focused on two heavy metals, zinc and nickel. Both of these are divalent cations, they're micronutrients, abundant in our environment, also present at hazardous levels in certain locations throughout the world. And they're really interesting to compare They're both, again, divalent cations. They're not redox active, and nickel is known to be a stronger Lewis acid than zinc. So we simulated an alluvial aquifer system by taking coarse and fine-grained sediments from a field site in Riverton, Wyoming. And then we simulated a homogeneous column with only sand, and a heterogeneous column containing sand and two fine-grained sediments that were embedded as spheres. And then we simulated a groundwater composition that was made to mimic the composition found at our field site with high concentrations of sulfate and nitrate. And here we focused on the behaviour of the heavy metal zinc that was introduced into the groundwater on day 21 of the experiment, which was continued for a total of 77 days. We monitored the poor water chemistry on a weekly basis through sampling ports located throughout the columns, and we also destructively sampled them at the end of the experiment for solid phase analysis. And here you can just see how this experimental setup actually looked like, and here is when we embedded that fine-grained lens into the sand. Okay, so here I'm now presenting the biogeochemical environment within our column systems throughout the duration of the experiment. So we have here 4 time points. We're looking at nitrite on top, sulfide, and dissolved organic carbon. The solid symbols here represent the heterogeneous columns containing the sand and the lenses. The hollow symbols represent the homogeneous columns containing only the sand. And here, the grey zones are highlighting where those two fine-grained sediments are located, and you have the column here on the right for some guidance. So, what we're seeing here is that we have elevated concentrations of nitrite and sulfide within the heterogeneous columns containing the lenses. Now, that shows us that we have a process of denitrification taking place. So we have nitrate that's being reduced to nitrite. Furthermore, you can see increased sulfide concentrations, and that's showing us that we have sulfate reduction to sulfide also taking place. And that shows that these lenses are sustaining reducing conditions both within them and in the succeeding sand. Moreover, we see higher levels of organic carbon released from the lenses, showing that they are also acting as a source of organic carbon.
Yeah. Clarification. The lenses are more like clay, and what size and what it contains?
So again, they were collected like from the field. So it's an oxbow sediment. So it's a really blackish, high organic matter content, a lot of clay. Generally sustains anoxic conditions even outside. So this experiment was conducted outside, not in a glove bag or anything.
What size are they? They're like a few centimeters? Or?
The spheres?
Yeah.
Yeah, just a few. I think it was like a diameter, maybe 2.5 centimeters. Okay. So, and then what I wanted just to highlight here is that you can see that sulfide disappears on day 21 of the experiment, and that can be attributed to the addition of zinc into the groundwater and the potential precipitation of a zinc sulfide phase. So moving on to pore water concentrations of zinc. So this is our heavy metal. The blue vertical line is showing you the concentration of zinc in the incoming groundwater. So based on that, we can see that we have accumulation of zinc in both the homogeneous and heterogeneous columns. But the accumulation or the retention of zinc is more substantial in the heterogeneous columns with those solid symbols. And that can be attributed to the presence of the lenses. But you can also see that the levels of aqueous phase zinc are negligible in the lenses themselves. So that raises the following question, which is, does zinc partition into the solid phase of the lenses, or does it simply bypass them? So for that, we're going to transition now into solid phase concentrations of zinc. And so here we're looking at solid phase zinc in a heterogeneous column on top, and an average value for a homogeneous column below. So this shows us that the zinc is indeed being retained into the solid phase. We see that for the sand, the levels are sort of more or less similar. However, for the lenses, we see that the first lens has accumulated nearly double the loading of the second lens. So this figure here shows us that zinc is indeed being retained, and at what extent, but we don't know the form in which it's being retained. So for that, we performed zinc extended X-ray absorption fine structure spectroscopy, or in short, XAFS. So XAFS is a really powerful tool to learn about the oxidation state of a metal as well as its surrounding chemical environment. So after collecting the data, you get these squiggly lines, and then what we did is we employed linear combination fitting in order to learn about the species distribution of zinc within our sample. So in linear combination fitting, essentially what you do is you use a set of reference compounds, and then you try different combinations of those compounds to reconstruct your experimental data. And here I'm showing the results of our fitting. So these red lines are overlapping very nicely with our experimental data, which proves to be a good fit. So our fitting showed that we needed 4 different zinc general species to describe the various retention mechanisms. So we have zinc layer double hydroxides, zinc associated with clay minerals, zinc complexed with organic matter, and a zinc sulfide phase. And you see here, just based on the colours, that we have a distinction between the sand and the lenses. So the layer double hydroxides and clay minerals are found throughout the column in both the sand and the lenses. You can see that in green and in red. However, zinc organic matter interactions were detected only in the sand, and a dominant zinc sulfide phase was present only within the lenses, likely due to a constant input of sulfate. So we have sulfate being reduced to sulfide, and therefore continuous accumulation of a zinc sulfide phase. And here I'd now just like to come back to the difference in the loading between the first and the second lens, and ask the question, is the zinc species distribution maintained between these 2 lenses? So I've hidden now the results from the sand, and we're only focusing on the 2 lenses, looking at the ratio between the first and the second lens for each of these zinc species. So for zinc sulfide, you can see that the level was maintained relatively the same between the first and the second lens. However, for the clays and layer double hydroxides, the loading was doubled in the first compared to the second lens. Now that implies that we have different retention mechanisms that are, or different forces that are controlling these retention mechanisms. So for the clays and layer double hydroxides, it appears that their formation is mainly dependent on the concentration of zinc in the incoming groundwater. However, for the zinc sulfide, it appears that there is a different force controlling this rate of accumulation. Most likely the rate of sulfide production, which is dependent on the activity of the sulfate-reducing bacteria. So these results show us that these lenses indeed influence the retention of heavy metals, or our heavy metal zinc. We see that we have different retention mechanisms in the sand and the lenses, with different controlling forces on these mechanisms of retention. Now, aquifers commonly tackle a combination of different contaminants. So we were interested to see whether the addition of a different metal would influence the conditions in the aquifer. Will zinc and nickel behave in a similar manner? Moreover, we wanted to see what the influence of nitrate would be on the aquifer biogeochemistry and heavy metal retention. So nitrate is a commonly used fertilizer, and it's definitely found at increased and hazardous levels throughout the environment, especially where we have intense agriculture. And that's really why we were interested to see whether it would influence the conditions and the retention of our metals. So just coming back a second to the aquifer setup, it's important to mention that both nickel and zinc were added to the same groundwater solution. For the influence of nitrate, we had a separate set of columns for nitrate-free groundwater and a separate set of columns for nitrate-rich groundwater, again to be able to distinguish between the two and see what the influence of nitrate would be. So we're coming back now to aqueous phase concentrations within our columns here, looking at nickel and zinc. Now, previously I've only showed you results for the nitrate-rich groundwater. That is now shown here in blue. I've added in the results for the nitrate-free groundwater in orange. And again, hollow symbols for homogeneous columns and the solid symbols for the heterogeneous columns containing sand and lenses. But looking at these figures, it's quite difficult to understand sort of what's going on, but essentially we can't really identify any difference between nickel and zinc, and it's really hard to see if there's really any influence of nitrate on the behaviour of these two metals. So after seeing these results, we wanted to look into the aqueous phase chemistry or focus on additional elements present in our system to see if we can even find any influence of nitrate. And then when we looked at aqueous phase concentrations of iron, this being the reduced form of iron, so iron 2, we immediately saw that there wasn't a clear influence of the nitrate presence. So here we can see that aqueous phase ferrous iron levels were consistently lower in the nitrate-free groundwater. Okay, you can see here that the blue symbols, I think I said the opposite, the blue symbols are consistently lower than the orange ones, so we have lower iron concentrations in the presence of nitrate. That suggests that the process of denitrification that's taking place in the heterogeneous columns in the presence of nitrate, so the denitrification is coupled to the oxidation of ferrous iron, which is taking out that iron 2 from the aqueous phase and moving it into the solid phase as iron 3. So after seeing these results, we were interested to look into the solid phase chemistry of iron to see what differences we could identify. So looking into solid phase iron, we use Mossbauer spectroscopy, which is, again, a really fabulous tool because it teaches us about the oxidation state of iron and the various species of iron that are present in our sample. So here on the left-hand side, we have the experimental data. This is only for the fine-grained lenses. So we have the experimental data before and after exposure to nitrate, which means that we have just the fine-grained lenses before the experiment, that's the before, and then after the entire experiment, so after the exposure to nitrate. On the right, I'm presenting the modelled data before exposure to nitrate. So the right-hand side simply teaches us about the different species of iron that are initially present within our sample. So we see here we have various iron oxyhydroxides, so we have hematite, goethite, ferrihydrite, a combination of iron 2 and iron 3 minerals, and also iron sulfide. But what was interesting here is that we found the presence of a distorted iron 3 phase. Now that phase was found to be more significant following the addition of nitrate, so after exposure to nitrate. That's shown here by the little red arrows. Now I know that looking at this here, it really doesn't look like there's any difference, but there is a subtle difference. It definitely exists, especially in the eyes of a Mossbauer expert, and that does suggest that the process of denitrification is resulting in a higher abundance of distorted iron 3 minerals. Okay, so after these results, we wanted to learn a bit more about the various species of both nickel and iron within our samples. So we performed some more XAFS analyses on the fine-grained lenses and coupled the data with what we found previously for zinc. So here I'm presenting the different species of these three metals in the fine-grained sediments. And you can see here we have some common pools of these metals. So we have the silicates in green and the sulfides in yellow. But there was a distinct difference in the third phase. So for iron, we have a specific pool of iron oxides, likely present due to redox oscillations that are taking place within the lenses. For nickel, we had a more significant contribution of organic matter interactions, whereas for zinc, more layered double hydroxides. Now, both zinc and nickel are prone to form layered double hydroxides, but strong nickel organic matter interactions are also known to hinder the formation of nickel layered double hydroxides. Now, how about the impact of nitrate on these species? So here I'm only showing the influence of nitrate for the pools that were present for all three metals. So we're looking at the silicates and the sulfides. So we can't really see a specific trend or a specific influence of nitrate on the metal silicates. But for the metal sulfides, you see the same trend where the presence of nitrate or the process of denitrification is resulting in a decrease in the metal sulfide pool, likely due to oxidation of sulfide minerals or the inhibition of sulfide formation. And these results here show us that the presence of nitrate is essentially resulting in a reduced capacity of these lenses to retain heavy metals, most likely because of a sensitive metal sulfide pool that appears to be most sensitive to groundwater composition and oscillations in redox conditions. So to summarise this theme here, I think that the most important finding is that the presence of these fine-grained lenses really does influence the retention of heavy metals and therefore the resulting groundwater quality. Now, even if the mass contribution of the lenses is small, their influence can be substantial, so they must be considered when we evaluate groundwater quality. Moreover, we have seen that the presence of redox-active species such as nitrate can further influence the accumulation of metals and also the form in which those metals are being retained. You're very welcome to look more into this study has already been published and it's focused on the behaviour of zinc, and the second manuscript here is focused on the impact of nitrate and is currently under review. Okay, any questions maybe perhaps sort of in the middle here?
So just a quick question about the lenses. They're organic, that's right?
Yes.
So are they different in composition from the coarse grain material, or is the coarse grain material also organic?
No, so the coarse is not organic rich, really low levels. Again, all these sediments were collected generally from the same site. So I'd say even if there are low concentrations in the coarse sediments, well actually I can't say anything about composition, never mind, erase that. But the levels in the sand were really low.
So what's the most important about them really is the composition rather than their texture? Would that be correct?
Sorry, could you repeat that?
What's most important is really their composition, the fact that they're organic rich rather than the fact that they have fine texture?
I think it's definitely a combination of both. You need the organic matter there for the activity of the bacteria that are, sustaining the reducing conditions. You can't sort of take, I think, those apart. Okay.
No, my question really would be if you put, say, silt or clay without any organic matter, presumably you wouldn't have the same effect.
No, I mean, you'd still probably have preferential accumulation of the metals because of the interactions, specifically with the clays, but you probably wouldn't see the impact of the sort of the redox environment. Okay, so what I've presented up until now are results from a lab scale experimental setup, and what we're going to do is we're going to progress now to a larger scale study of a field system and focusing on subsurface heterogeneities of a floodplain. Okay, so our next theme is on the structure and dynamics of colloids in our floodplain system. So this is our field site in Colorado. This is Slate River in Colorado. This picture was taken in September of 2021, not by me. But the arrow here shows the specific sampling location I'm going to present results from today. And this study is part of a wide group effort, which is the SNAC SFA, which is the group I'm a member of now, which is a really fabulous group because we try to put together the hydrology, microbiology, biogeochemistry, and modeling to have a broad understanding of the floodplain system. But again, I'm just going to focus on this specific site for today, showing results from the 2021 season. And so again, we have this really fabulous and lovely landscape. You see some surface water, but we're going to look down into the subsurface of this site. So here the subsurface can be separated into layers or into zones based on the sediment composition and a degree of dissolved oxygen. We have a shallow oxic layer followed by a zone of where we have fine-grained sediments where anoxic conditions dominate, and below we actually have a flow of oxygenated groundwater. So here you can see we have some really interesting and unique interfaces that contribute to the reactive and dynamic conditions at the site. Our group has been monitoring both the hydrology and the poor water chemistry for several years, and today I'm just going to focus on some results from the 2021 season. So in spring months of May and June, we detected high concentrations of reduced iron-rich colloids. So here I'm showing the concentration of colloidal ferrous iron as a function of depth. And you can see here really high levels that were detected in the anoxic zones. We define colloids to be in the 20 to 220 nanometer size range. Now, colloids are really unique. They don't exactly behave like dissolved species. They can interact with nutrients and organic matter and therefore transport them throughout aqueous systems. And their composition and reactivity will dictate their role as exporters within the environment. And that's why we were interested to decipher the structure and composition of the colloids. So we started to characterize them from the nano to micron scale. Is it supposed to be red?
Sorry? Oh no. Can you press it?
Now it's red.
Let's keep on going.
Okay, sorry, I just noticed that. But that's green, never mind. Okay. So we characterized the colloids from the micron to nanometer scale, and we started with cryo-electron microscopy. Now, I love cryo-electron microscopy because it just gives you a picture of your sample just as it is in the aqueous phase without any disturbances due to drying or filtering of the sample. And we were really, it's quite difficult, I think, to see from where you're sitting, but we did identify all these sort of spherical blobs in a variety of shapes and sizes. And you can also see elongated structures of these colloids that seem to be made out of multiple spheres, so sort of these nano assemblages. And addition of a smaller filter size of 1 to 3 nanometer validated that the colloids are indeed mostly larger than 1 nanometer in size. So this gave us some initial insight into the size and structure of the colloids, but we wanted to learn more about their composition. So we continued with transmission electron microscopy coupled with energy dispersive X-ray analysis to learn about the elemental distribution in our sample. On the upper left here you see just again this colloidal assemblage with those sort of multiple spheres making out the whole colloid. And then we detected high contribution of iron, silicon, oxygen, lower but still substantial levels of carbon and calcium, and also some contributions from sulfur and aluminum. And these images suggest that our colloids are composed of iron minerals, clays, and organic matter, probably with bridging cations such as calcium. We were quite surprised by how high the oxygen levels were, because that suggests that we have iron oxyhydroxides present. And then we collected diffraction rings using the TEM, and the D spacings here were actually consistent with two-line ferrihydrite. We were also able to collect some Mossbauer data of the colloids, and fitting of the data showed that we have the presence mostly of amorphous iron minerals, likely ferrihydrite, with different coatings of organic matter and silicon. So the Mossbauer and the TEM data complemented one another very nicely. But I want to stop and recollect a second that we initially detected these colloids because of high levels of iron 2, of ferrous iron. But I've just shown you that we have a high contribution of ferrihydrite, so iron 3. And that raises the question, why do we have oxidized ferrihydrite-like colloids that are abundant in anoxic reducing conditions? And it appears, especially from the literature, that coatings of organic matter and silicon can actually protect iron minerals from redox processes. And if you look at the overlap of iron, silicon and carbon, it does really seem that the carbon or the organic matter in the silicon is coating the iron. So it's coating the ferrihydrite, serving as a protective layer against redox processes. So these colloids, or the abundance of the ferrous iron colloids, was most significant in spring months of May and June. But look what happens in July. There was a distinct drop in the concentration of iron 2 colloids, or in the contribution of iron 2 to our colloidal assemblage. So again, now we're really interested to try and understand how exactly is the iron 2 associated with our colloidal assemblage. So we performed some more iron XAFS spectroscopy to learn about the oxidation state in various species of iron in our sample. Here I'm presenting the XAFS data for the June and July samples. This is at 180 centimeter depth. And on the left here is the derivative of the absorbance, which is, shows us about the oxidation state of iron. So you see here in both June and July we have a combination of iron 2 and iron 3, but higher abundance of iron 2 in June and higher abundance of iron 3 in July. So we know that the iron 2 is mostly, or most likely, ferrihydrite, but we don't know about the iron 2. So we employed some more linear combination fitting on these samples. You can see the results of that fitting here in the red dashed lines. The July fitting is a really good fit. The June fit still needs to be improved a bit more, and we're working on that. But despite this, these results are satisfactory to learn about the differences and the trends between these two samples. So the fitting showed that we had 4 main species of iron: ferrihydrite coated with organic matter, iron 2 complex with organic matter, and iron 3 complex with organic matter. Now that first of all validates all the previous results that I have shown you, that ferrihydrite is a significant contributor to the colloidal assemblage, and also that we have a contribution of organic matter interactions. It also shows that the iron 2 is most likely present due to organic matter interactions. Now, comparing between June and July, we can see that there is a lower contribution of ferrihydrite in June, and that the iron 2 organic matter interactions are nearly 40% of the total iron within the June sample. However, in July, you can see those trends are reversed. We have an increase in the contribution of ferrihydrite and a drop in the contribution of iron 2 organic matter interactions. These go down to be merely 11%, showing that the colloids, the July or summer colloids, are more oxidized in nature. So these results here really exemplify the dynamic and delicate composition of these colloids. I think that the most important finding of this study is that we have detected natural oxidized iron-rich colloids that are abundant in anoxic-reducing conditions. We've also seen that the composition is highly dynamic and seems to be very much dependent on the season. So we're working on summarizing this now into a manuscript that's going to be focused on the characterization of these colloids. We're also working on linking the dynamics, or the colloid dynamics, to our results on hydrology and pool water chemistry at the field site. So anyone who's interested, stay tuned. Okay. Any questions?
So what explains the seasonality?
So I don't want to skip. Wait a minute, I can show you some figures afterwards that are not part of the entire presentation. But what we're seeing is that it appears that in spring we have a lower downward pore water velocity. So it seems that the residence time of the colloids in the anoxic zones is longer. So we're hypothesizing that there's just more time for reactions to take place. So, I'm not sure exactly about the kinetics, but it's probably a slow process that's taking place. And that's why we see more reduced iron in spring. And we're also seeing higher organic matter concentrations in spring after snow melt that's pushing down the organic matter. And then the organic matter concentrations are decreased throughout the season due to degradation. So we're thinking that there's also less of that protective layer. Those are things that we're working on now. All right. Okay, so I wanted to vote just a few more minutes to present some of the future research that I'm interested in doing. I hope to open a lab that's going to be devoted to biogeochemical heterogeneity in a dynamic environment, really focusing on biogeochemical cycling of elements in heterogeneous subsurface systems, looking into the influence on soil and groundwater quality. Again, I hope to employ or to use lab-scale experimental setups coupled with advanced analytical and characterization methods to learn about the processes taking place in the subsurface. And here I'd like to come back to this image here, really to emphasize the importance of biogeochemical cycling. So all of these cycles, how they perform, how they interact with one another, and how the cycles are influenced by surrounding conditions and climate, is really going to influence the services that they provide us on a daily basis, such as clean water for drinking and irrigation purposes, fertile soils to grow crops, and therefore in terms of food security. So I think that understanding the processes and reactions taking place in these systems is really indispensable and important to further understand. I would like to focus on three main research themes: realms of heterogeneity, functional heterogeneity, and dynamics of heterogeneity. So the first theme, realms of heterogeneity, the guiding question here is going to be: how do varying spatial and compositional heterogeneities influence the cycling of key elements? So I've shown you throughout this talk how both spatial and compositional heterogeneities can influence groundwater quality. But how heterogeneous can these systems be? So what happens if the size, the distribution, and the structure of the sediments is different? What happens if the composition of those sediments is different? And here I would like to look into the general biogeochemical function. So that's the diverse set of reactions and processes that are taking place in the subsurface and controlling groundwater quality. I'd like to look into the temporal effect, so focus on the kinetics in both the aqueous and in the solid phase. I'm also interested in the contribution of groundwater composition to represent different groundwater sources. So all of these can have different pH values, organic matter contents, ionic strength, dissolved oxygen concentrations. I would like to look into dynamic flow regimes, so constant versus oscillating groundwater flows, trying to link also the impact of hydrology. And I think that the main impact of this research theme is understanding the mechanisms, the kinetics, the rates of the reactions and processes that are taking place within a heterogeneous subsurface system. The second theme, functional heterogeneity, the guiding question is what is the relationship between particle size, composition and reactivity, and how will these three relationships influence particle transport. So this is essentially a continuation of theme 1, but looking more into what controls the processes at the particle scale. So here I'm really interested to look into the role of the various mobile particles within the subsurface and how they contribute to biogeochemical cycling. First, I would like to look into the importance of particle size, looking into particle size distribution. So what really is the distribution between dissolved, complex, colloidal, nano, and particulate particles? How will that distribution change in different systems, and how will the distribution be influenced by surrounding and changing conditions? Now we know that particle size is an important factor in a particle's transport through porous media. Also, I would like to look into the importance of particle composition. So if a particle has changed its size class, or why exactly has a particle changed its composition when it transfers between different size classes? We know that the composition is also a dictating factor in a particle's transport. Now, if a composition of a particle has changed, that suggests that it has reacted somehow with something. So what exactly has made our particle transport? What reaction has taken place? How will a particle's reactivity influence its transport, or how does a particle's transport influence its reactivity? Now, this is all highly complex, where we have heterogeneous systems with a multitude of reactions that are taking place, which makes studying these systems really challenging, but also very much intriguing and compelling. And here the main impact is going to be understanding a particle's life cycle, so a particle's dynamics, really understanding what happens to a particle in heterogeneous and changing conditions. And the third theme builds again on the previous two, adding in a dimension of dynamics, because we have changing and shifting conditions in our environment. Those changes may be seasonal, they can be accidental, they can be natural, they can be anthropogenic. And here the main guiding question is, how do hot moments influence heterogeneity function, cycling of chemical species, and groundwater quality? Now, a hot moment can be described as a sudden change or event that triggers or enhances a specific process. So a hot moment can be a specific event, such as an intense rainfall period, a contaminant spill, a wildfire, but a hot moment can also be something that occurs seasonally. So addition of fertilizers, organic matter leaching, following snowmelt or groundwater pumping. So I would like to look into the biogeochemical response to specific hot moments. Which processes are most vulnerable to specific hot moments? What exactly will the result be? How long will that result take place, and is it even something that's irreversible? So here the main impact is going to be better understanding of how elements are cycled in dynamic and changing conditions. And that's particularly important due to the challenges that we all face with industrialization, population increase, and climate change. So that's a broad overview of the research themes that I am planning on looking into in the future. I'm very happy to discuss these themes more and also specific research projects that I have planned. But with that, I would like to again acknowledge all the mentors, collaborators, colleagues, especially mention my collaborators at SSRL for all the XAFS work, so Vincent Noel and Juan Lezama Pachico, and also my really wonderful collaborators at MCEL, so Libor Kovarik working on the TEM, and Ravi Kukadapo on the Mossbauer. So these are all ongoing collaborations that are really important to my work. Also say a big thanks to my mentors and mostly mentors over at the Faculty of Agriculture, and then finish with some photos of life at Stanford and some family, and thank you all for your attention.
Thanks so much. Questions?
Okay, ich habe schon mal so Kari
I have one. Or is that the question?
Sure.
Yeah, go ahead.
Nice talk. I wonder from how do you plan to go from the lab scale, which is naturally small, or even the single site in Colorado, to upscale it to real natural systems?
Yeah, so that's a super relevant question. So first of all, I am very much interested in the fine scale, so particle level, and in those, sometimes in those cases you do need to work in, I'd say more in smaller, at smaller scales and resolutions. But even when you think about the experiments that we've done on the fine grain lenses, so that already teaches you a great deal about what happens in an aquifer. So I can't look and map an entire aquifer now. It's huge. So, but if we know how the presence of these lenses influences groundwater quality, perhaps we can tailor where exactly groundwater pumping, or when we perform groundwater pumping. If you know that there's a higher accumulation of contaminants in fine-grained sediments, and that those can be released in certain conditions, or if we have a pulse of oxygen or something, then that fine scale already teaches you a lot about the big scale. And also simple sampling at the field scales, like what we've been doing, understanding the colloids. That also shows you a lot about how at certain seasons the amount of iron that's in colloidal form can be nearly 25 or 30% of the iron at specific seasons. And then if you further investigate how that impacts the transport of iron, that can help to understand fluxes of nutrients in the environment. So I think that, anyway, that you can learn a lot about, even if you don't actually do huge studies. I mean, yeah, okay.
Questions? So where exactly do these very colloids get coded by organic material? Where, when?
Well, a lot of these systems, are sort of natural, and it's millions of years of formation of all of these soils. But as you have seasonality in terms of leaf litter and just organic stuff, that you have on the surface, and that gradually is degraded and sinks into the soils, then you have additional accumulation of organic matter that enhances or fuels various reactions, both biotic and abiotic. I'm not sure if that exactly answers what you asked.
But in the oxic zone of the weathering zone profile, that's where you have it. Is that where, I wonder if they get coated relatively high up the section and then get mobilized to the region.
That can definitely be part of it, but we have less iron at the shallow depths. So I'm pretty sure that we have a layer where we have a lot of iron, and then we have organic matter that's pulsing in, complexing with the iron, and then with all the redox oscillations, then you have ferrihydrite. Again, this is all sort of me, hypothesizing out loud. I'm still not sure how to explain everything, but I'm not sure, but it's definitely, we definitely think there's a really important role of the organic matter that's complexing the iron, and then with redox oscillations, you have oxidation and probably precipitation of ferrihydrite, and then, something of that sort. But if anyone has ideas, then I'm happy to hear.
No, an alternative hypothesis would be that it's getting coated by, it's being produced in the soil section, the organic material, and some, microbe maybe for microbial activity or some sort. But
if I may say, this issue of interaction of iron and organic matter in the surface has been studied for 100 years. There are probably hundreds of papers about it. It's not nothing novel. People have been doing it in Canada, in the US, in Europe for a lot of years. It's been studied heavily.
Yes, that's true. We're not looking into, the goal of this study is not to show, novel iron organic matter interactions. We're trying to explain trends of why we have seasonality in specific species of iron. So why do we have these colloids present? So yes, we're trying to base what we're doing now on previous studies to understand why we have these colloids present.
All right. Any further questions? So let's check.